Up to this point, we have covered what I consider to be the four major physics principles in this course, namely kinematics, Newton's second law, conservation of energy, and conservation of momentum. We applied these principles in linear applications so we can further specify them to be linear kinematics, Newton's second law dealing with linear variables, conservation of energy, again dealing with linear variables, and conservation of linear momentum. Even when we addressed circular motion, we applied Newton's second law to centripetal force and centripetal acceleration, and these are still linear variables. In the next few videos, we'll discuss rotational motion and apply these same four principles to the angular variables involved. When we do that, linear kinematics becomes angular or rotational kinematics. When we extend Newton's second law to angular variables, we will refer to it as rotational dynamics. We will expand the conservation of energy to include rotational kinetic energy, and we'll discuss the conservation of angular momentum. So now let's discuss rotational kinematics. With rotational kinematics, there's a strong parallel to linear kinematics, so let's quickly review that process. As an example, let's consider a ball that is thrown up into the air and then falls back down like this. Using kinematics, we might find the final velocity of the ball, given, say, the initial velocity, the acceleration, and the time. The basic process is to list the 5 kinematic variables, select the ones that apply to the problem, and then solve the applicable kinematic equation. So that's an example of linear kinematics that deals exclusively with linear variables. We are now interested in describing circular or rotational motion, such as a rotating bicycle wheel or the orbital motion of the Earth around the Sun, something like that. To do this, we will apply similar equations and techniques to describe rotational motion that we just applied to linear motion, but we will replace all of the linear variables with the corresponding angular variables. So here are the 5 linear kinematic variables again, and we'll replace them with the equivalent angular variables. When we replace the variables in the linear kinematic equations with angular variables, we then get this set of angular or rotational kinematic equations. Just as with the linear kinematic equations, these equations are only valid when the angular acceleration is constant. And as a method to select the correct equation to use, we can again recognize that each equation is missing one of the 5 kinematic variables. Notice one difference between linear kinematics and rotational kinematics is that the linear equations are vector equations, so we apply them in the x and y directions separately. With rotational kinematics, we're just dealing with rotational motion, and so we just have the one set of equations shown here. When we apply rotational kinematics, we will follow essentially the same procedure that we did before with linear kinematics. Specifically, draw a simple diagram that shows the initial and final positions of the object, the rotational kinematic variables, and then list the 5 rotational kinematic variables, including the data that were given, and then choose the applicable rotational kinematic equation and solve it for the unknown. And then finally, as usual, make sure that your answer is reasonable. To demonstrate this process, I'll work through a simple example. Say we have a carousel that's rotating counterclockwise when viewed from above with an initial angular speed of 0.2 radians per second. If the carousel slows with an acceleration of 3.5 times 10 to the minus 3 radians per second squared, how long will it take for it to slow down to 0.1 radians per second? So there's our diagram, and now the next step in the procedure is to list the 5 variables and include the information that was given. Notice I've applied the sign convention that counterclockwise is the positive direction and clockwise is the negative direction, which is why I made the velocities positive and the acceleration negative. We can now recognize that these are the 4 variables involved in this problem. And so we can select the rotational kinematic equation that involves these 4 variables. And then solving this for time and plugging in values, we find that the time is 28.6 seconds. So that's the process for rotational kinematics. You can see that it is nearly the same as the process for linear kinematics, so it should seem pretty familiar to you. And so that's all I wanted to cover in this video. In the next few videos, we'll continue to discuss rotational motion and apply the other major physics principles that were mentioned earlier. So see you then.